So again, this equation that's up on the smartboard is one that's given to you. However, you're not going to end up using it to do any sort of math. It's odd that they give this to you on the equation sheet, and yet you're really not going to do it when it comes to math. What I want to do is in my notes, if you read our textbook dealing with the speed of gases, it's going to show you a couple of different equations that are not given to you on our equation sheet. I want to try to draw a correlation between the equation up on the board and those equations that are typically more often given in text when describing how gases are moving around. That way, hopefully you'll be able to kind of see what you would need to know when dealing with these gases. Now, one of the equations that's given in most textbooks is what's called the root mean squared equation to go over speed. I don't know why some textbooks use a U instead of a V for the speed as opposed to velocity. I'm wondering if that's to deal with the fact that velocity also has direction as one of its components, and speed is not based upon direction. But they give this equation of the square root of 3RT over M. Now, another reason why I like to go over this, even though I don't think you're going to use this specific equation on any test, one of mine or one of theirs, it introduces us to ideal gas law constants. Capital R is a constant. Just like pi is a constant, it makes circle math work. That's my definition of pi. I think it's a fairly solid one, right? Without pi, you can't do radius pi, you can't do that stuff. R makes a lot of gas law math work. The reason why I show you this number up on the smartboard is this number, even though that equation is not given to you, that R value is given to you on your equation sheet. And what I can tell you is you're probably not going to use that R value. And what's weird is they give you two other R values on it as well. Depending upon with gases what thing you're solving for, R changes. And that is different than pi. Pi is just 3.14. It doesn't matter. Circle, sphere, that's what pi is. It doesn't matter if you're trying to figure out circumference, you're trying to figure out area, you're trying to figure out volume. The nice thing with pi is it is just that one number. Unfortunately, with gas laws, there are a few different types of R's, and they're all unit dependent. So it's common that students will look at their equation sheet to find R to plug it into an equation that they will need to know called PV equals nRT. We'll go over that next week. But they might pick the wrong R value. And this R value is dealing with energy. That's why joules is involved in its unit. So we're going to avoid that. And again, it gives a conversion between joules and kilojoules mass. I don't care about that. That squiggly M is molar mass. So I'm not going to solve this problem. I'm not going to give you a sample problem with this because you're not going to have to see any problem with this. Here's why, besides the R thing, I'm going over this first slide. And again, if you looked in your textbook, it would talk about the root mean square equation. In order to solve for the speed, which they say is that U of RMS, root mean squared, that speed, you have to take the square root of things including the temperature and the molar mass. Temperature has a direct relationship between how fast things are moving. You saw that hopefully in the packet. That's why temperature is involved. The size of the particle has a direct relationship between that as well. But lastly, it's a square root. And if you remember on the first slide, kinetic energy is 1/2 mv squared. Well, to undo that squared, you have to take the square root. That's what this is showing here. So I don't think it's as important to know this equation. However, this idea of a square root is what I'm going to show you on a second equation that our textbook always goes over, that once again is not given to you on your equation sheet, but you have to be vaguely familiar with. So the point of this first slide isn't that you memorize any of this. Again, this R value would be given to you, and I'm telling you right now, steer clear of this R value for most things. This equation right here is not given to you, and you're not really going to need to use it, but what you could do is if you knew the molar mass of a gas and the temperature that it was at, you could calculate the speed in meters per second of that gas molecule. Okay. When we mix two different gases, this can be referred to as diffusion, just like in diffusion has definitions dealing in a biology sense. You know, plasma membrane, what's crossing that to try to get to equal concentrations of things. The movement of gases, where they're able to mix, is referred to that diffusion. And what I'm going to do right now is I'm going to, again, go back to the old textbooks Animation Center and show you a quick video that they have to try to explain diffusion. And in that process, they are going to show a second equation that relates the speed of two different gas molecules. Not tonight's WebAssign, but next time's WebAssign, I am going to ask you a question about the speed of gases and how they compare mathematically. The equation that this video is going to bring up at the end is going to kind of go over that, and I will show that on my following slide.
Provided by diffusion, the gradual mixing of molecules of one gas with molecules of another gas. In the apparatus shown, an aqueous ammonia solution is injected in the left side of the tube, and at the same time, aqueous hydrochloric acid is injected on the right side. Ammonia gas diffuses from the left, and hydrogen chloride gas diffuses from the right. The two gases combine to form ammonium chloride, a white solid. Note that the ammonium chloride forms near to the right side where the hydrochloric acid was injected. We zoom in to show the reaction on a molecular level. In 1832, the Scottish chemist Thomas Graham found that under the same conditions of temperature and pressure, rates of diffusion for gases are inversely proportional to the square roots of their molar masses. This statement, now known as Graham's law of diffusion, is expressed mathematically as R1 over R2.
And I'll show you that equation in a little bit.
M2 over M1, where R1 and R2 are the diffusion rates of gases 1 and 2, and M1 and M2 are their molar masses respectively. Because ammonia is lighter, it will diffuse faster than hydrogen chloride. A quick calculation shows that ammonia diffuses 1.46 times faster than hydrogen chloride.
So, the math that they're showing here, I'm going to go over in a little bit. But basically, what I have seen in the past when we're dealing with the rate of gases and how fast they're mixing, or this one goes through a pinhole this quickly, how fast does this one go through a pinhole, is when you relate the molar mass of the two gases in question, recall that smaller gases will move faster than bigger gases. However, when you look at their calculation here, it is not just taking the mass of the big divided by the small and saying that the small is 2 times faster, which is basically what 36 divided by 17 would give you roughly. They're saying it's the square root of that ratio between the masses of the things. And that goes back once again to 1/2 mv squared, where it's mv squared. So if you need to compare two things, you need to take the square root. What I have seen for questions in the past is they'll give you something with a molar mass of, let's say 80, and another thing with a molar mass of 20. And they'll ask which one is faster and by how much faster. And this is math that they would expect you to do in your head. Realizing that the thing with a mass of 20 is smaller, most people would say, hey, it's faster. Good. However, a lot of students would say that the thing with the mass of 20 is 4 times faster than the thing with the mass of 80 because it's 4 times smaller. However, Graham's law is dealing with, it's not just the ratio of the molar masses, it's the square root of that ratio. So in the example I give of 80 over 20, 80 divided by 20 is 4, but if you take the square root of that, it's actually 2 at that point. So the gas that has a mass of 20 for the molar mass would actually be twice as fast as the other one. That is the one type of little bit of mental math that is kind of expected of you. I know I have one question on web design next time dealing with that, but that is what we need to be aware of. So here is that Graham's law. The rate of gas 1 over the rate of gas 2 equals the square root of the molar mass of 2 over the molar mass of 1. And R's are the rates, how quickly they're moving. M's are the molar masses. Again, this equation is not given to you. However, we can kind of mentally use it as I was describing. First off, smaller gases move faster. That's something we need to be aware of. Secondly, there is an actual mathematical relationship between how fast one gas is moving versus another. And that relationship is going to be dealing with not just the ratio of their molar masses, but the square root of their molar masses. Now, I'm not going to want you to write down this next part here because, again, looking at the new standards, this next little tweak to this equation I don't see pop up anymore. But sometimes they will refer to how much time it is. So how long does it get from point A to point B? So how long does this gas take versus that gas take? Smaller gases are faster, which means it should take them less time to get from point A to point B than larger gases. So keep that in mind as well, that this equation isn't meant to be used as much as an equation. It's more meant to be used as a way to remember smaller things are faster, but it's not just that, it's the square root of their molar masses that determine that speed. So they define diffusion as the mixing of the gases when they come together. The other way gases are measured sometimes is what's called effusion, is when we are finding out how long it takes a gas to escape. And mathematically, it works under the same principles as Graham's law. And the example I like to talk about is a helium balloon versus a balloon with normal air. If you were to let the air out of two separate balloons, one being helium, one being normal air, the helium balloon will deflate faster because its gas is lighter. It's smaller than the molecules of air. Smaller molecules will move faster. Again, if it was pure oxygen versus helium, O2 has a molar mass of 32 grams per mole. Helium has a molar mass of 4 grams per mole. So you can divide those two. 32 divided by 8. 32 divided by 4 is 8. Take the square root of that. I don't know, that's 2 point. So it would be a little over 2 times faster, a little under 3 times as fast as it would leave the balloon. It would deflate faster. So when we deal with gas speed, that's what we are looking at. We are looking at how fast one gas is moving than the other. And the key here is to realize it's not just based upon molar mass when we're trying to figure out that ratio. It is going to be molar mass with that square root component. Now, what I would like to do to wrap this up is that that worksheet you picked up on the way entitled Diffusion and Effusion. I'd like to go over one question with you on that to kind of show you the math anyways, even though you shouldn't anticipate doing this specific math unless it's more of a mental math, would be my hope. So on that worksheet, I'm not going to do numbers 1, A through F. That's something I'd like you to just do on your own of which one is going to move faster. Hopefully that is relating to what we've gone over today. I'm going to do question 2, and I'm going to stop at that. Number 2 says an unknown gas effuses at half the rate of carbon dioxide. Find the molar mass of the unknown. Again, this is Graham's law equation. And what what it states is, or what's asking us to find is the molar mass of an unknown. So we're going to find the molar mass of something. We already know the carbon dioxide molar mass. Carbon dioxide, CO2, 1 carbon, 2 oxygens. That's a little over 44 grams per mole. But if you read the question, it says an unknown gas effuses at half the rate of carbon dioxide. First off, that means it's slower than carbon dioxide, which means it's bigger than carbon dioxide. So one of the things that we could do then is we could call that R1 0.5 rate of CO2 divided by what's the rate of CO2. Mathematically then, this part cancels out. You okay with that? This would equal the square root of the molar mass of carbon dioxide, which is 44.01, over the molar mass of what we're trying to solve for. To solve for that m, you'd have to take the square of both sides to get rid of the square root. Multiply by the m1s, get m1 by itself. I end up with 176 grams per mole. Now that's how Graham's law would solve it. If you think about it in terms of the square root idea, however, if it's half as fast, half the rate, that means carbon dioxide is twice as fast as the other thing. Does that sound okay? One thing is half as fast, the other thing is twice as fast in comparison. So, if I know that carbon dioxide is twice as fast as mystery gas, then what I could do is I could think about doubling this, but that's not enough. I have to take it times 4 because of that square root. So if I simply took 4 times this, I would get to that number anyways. So the Graham's law equation is useful, especially when it's not nice and neat, 0.5 or 2, if it's like a 1.1 or a 3.3. You can't do that mental math as easily. But overall, identifying that small gases are quicker than big gases, and that it's not just molar mass, it's the square root of the molar mass is what the goal is of this section here today.